Howdy everyone, welcome back for Chapter 4 example problems where we will talk about solutions, the ions in them, and how we use the concentration of solutions. So for the first example, and this comes up a lot on various problem sets or on tests a lot. I've seen it on, I've put it on exam 2. It sometimes even affects exam 3 and probably the final as well. ACS loves these questions. Where it's just, here's two ions. Will a precipitation occur? Will one of the products, when we do a double replacement reaction, be insoluble? So to do these, all you need to do is say, okay, I got my two compounds. When they switch ions, what will the products be? And then you check your solubility rules. It is helpful before you switch them to still use the stuff from chapter 2. Say, what would the charges be? That way I know I have the right formula at the end. Because sometimes you're also asked to balance the equation. So you might as well do it right from the beginning, and that way you have all the information you need. So sodium is always +1. CO3 is carbonate, a polyatomic that's -2. Silver is always +1. Nitrate is a polyatomic with -1. So when we switch these, we'll say, okay, we're going to get sodium, that's +1. We'll pair with nitrate, that's -1, so one of each. Silver is +1. Carbonate's -2. When we switch, we will get 2 silvers and 1 carbonate. But now we look for the rules. Will they be soluble or insoluble? So in this case, sodium nitrate. But sodium is one of the rules that was always soluble. Nitrate's always soluble. This thing is going to be aqueous no matter what. Silver carbonate. Carbonate was a rule of it's almost always insoluble unless it's with an alkali metal. Silver is not an alkali metal. This is going to be solid, which means yes, precipitation does occur. If we look down here at letter B, again, sodium's +1, nitrate's -1. Nickel, don't know, it's a transition metal. Got to look at the other half. Sulfate, -2. That means the nickel has to be +2. When you do a double replacement reaction, the charge of the transition metal does not change. So if it's +2 here, it'll be +2 when we switch. So it'll be nickel. We'll need 2 of the nitrates, so put that in parentheses. Okay. And then we have sodium with sulfate, so +1 with -2. So this will be 2 sodiums and 1 sulfate. Now, I'm not balancing with coefficients, but these are the right formulas. You could put numbers in front to balance if you want. With this one, okay, nitrate, we just said, always soluble, no exception, so that's aqueous. And then this one, sodium, always soluble, no exception. So both are aqueous. That means no, precipitation will not occur. Nothing's going to be a solid. All right, finally part C. Again, don't know with iron, it's a transition metal, but I do know with sulfate it's -2, that means the iron's +2. With lead, same thing, it's not a transition metal, but it still has various charges, we don't know. But we do know that nitrate's -1, because there's 2 of them, that adds up to -2, so the lead has to be +2. All right, so now when we say, well, what will the pairings be? Iron's +2, nitrate's -1. So we'll have iron with 2 nitrates when we do that crisscross. Then lead, we have lead is +2, sulfate's -2, so that's 2 and 2, reduces to 1 and 1. So it'll be PbSO4. Now we apply our solubility rules. Nitrate, always soluble, aqueous. Here, lead sulfate. Sulfate, usually soluble, but we have a couple exceptions of calcium, strontium, barium, and lead, which means, oh, that's a solid. Lead was the exception. So yes, with a solid, yes, precipitation occurs. So A and C, we would get a precipitate. Letter B, no, we would not. Okay. Next one, net ionic equations, where we first balance a complete equation, but then we'll reduce it to say, well, what splits up that's aqueous? What doesn't split up, that is either a solid, gas, or liquid, and then see what cancels out. So same thing that we just did. First we got to switch. So hydrogen's +1, bromine -1, calcium is always +2, hydroxide's -1. Now we can switch. We'll have calcium with the bromide, so that'll be Ca Br2. And applying our rules, bromide, we had the rule always soluble except for silver, lead, and mercury. That's not calcium, so aqueous there. And then our other product, we have hydrogen plus 1, hydroxide minus 1. Well, that's HOH, better known as water, which will then put liquid. And so then we just need to balance. Here we have 2 hydroxides and we need 2. So it looks like you need to put a 2 there. And then that means we have 4 H's on the left, so we need 2 there. So it's 2, 1, 1, 2 for our balancing. So that's the net ionic. Or sorry, that's not the net ionic. That's the molecular form equation. Now we want to go to the total ionic and then simplify to the net ionic. So for the total or complete ionic, we break it all up. So HBr is a strong acid. It does separate completely. So we'll have H plus aqueous, and there should be 2 of them from the balancing, right? That 2 distributes, so 2 H pluses, 2 Br minuses. We'll have a calcium 2 plus. We will have 2 hydroxides, so that little 2 right there. Still all aqueous. There's our arrow. All right, calcium bromide aqueous, so another calcium plus 2 aqueous, and now we have 2 bromides because of that little 2 there. And now water is liquid, so it does not split up. Liquid, solid, and gas does not split up. So we'll just have 2 water liquid. All right, and then that will let us do our net ionic, where we say, well, what's the same on both sides? That'll cross out. Well, calcium's the same on both sides. The 2 bromides are the same on both sides. So what we have is 2H plus aqueous and 2 hydroxide aqueous becomes 2 water liquid. Then it is common if you have 2, 2, and 2, go ahead and simplify. So we'll just say H plus aqueous, hydroxide aqueous goes to 1 water liquid, and that is the net ionic equation, which is good because that's an acid-base reaction, and acid-base reactions for the most part will have this as their net ionics. If there's a weak acid, those don't split up, so some of those won't cross out, but for strong acids, strong bases, it always goes to this. Okay. Next one, we're moving into molarity. So it says how many milliliters of a 6 molar sodium hydroxide solution are needed to provide 0.350 moles of sodium hydroxide. So the key to remember is that molarity is always equal to the moles of solute divided by the liters of solution. In this case, we're trying to find volume. We're trying to find milliliters. Now that's liters, but we can get there. So we want to rearrange this equation first to say that the liters will equal the moles divided by the molarity, right? We just did cross multiplying. You know, whenever you go across the equal sign, you flip numerator and denominator. So we have moles to plug in. We have the molarity to plug in. We're going to solve for liters. Then we'll go ahead and make it milliliters. So the liters will be the 0.350 moles that we want. We will divide that by the 6.00 molar solution that we're given. So 0.350 divided by 6. We get an answer of 0.0583 repeating, so it just stays 0.0583 liters. Then to convert that to milliliters, if you hopefully have the metric system in your head, you can just move that decimal the 3 spots. But if not, remember that there are 1,000 milliliters in 1 liter. That will cross them out. We'll multiply by 1,000, so you get 58.3 milliliters as your final answer. So a lot of times with molarity problems, that's what you end up doing. They always give you 2 of the 3, and then you might have to rearrange the equation, solve for what you're missing, and then sometimes, okay, yep, got to move that to milliliters. It's also common to solve for moles and then have to turn the moles into grams. That's a very common thing. Or be given grams, turn it into moles first, and then plug it in. But, common forms. All right, last problem is molarity in a stoichiometry problem. So this is a titration problem where there is a equation that I may share in class with you, but this one we're going to show it as if we're doing just normal solution stoichiometry, where we'll plug it into our three-step equation. The one thing we'll do is we'll just say, okay, remember that milliliters, we got to use liters for molarity. So 50 milliliters, we're just going to say that is 0.05000 liters, and just kind of do that in our heads, or do the same dimensional analysis we just did on the last problem to, in this case, divide by 1,000. All right, but if we start over here on the left, we always want to start with our given, which in this case is the 50 milliliters. It is the 0.50 liters. Remember, molarity is moles per liter. It's a conversion. We start with the liters because that's not a conversion. That's just a given thing. So 0.05000 liters. In this case, we will put NaOH because we want to make sure that we know which chemical is which. Now we use that conversion. Liters will go on the bottom, moles on top, and the molarity is how many moles per liter. So it's 0.0875 moles of NaOH for every 1 liter of NaOH. I'm just realizing here, hey, we need to balance this equation because it wasn't given to us. So in this case, let's do that real quick. HClO4 plus NaOH. Again, it's an acid-base reaction, so that'll make this easier. We'll get sodium perchlorate and water, and it looks like, hey, that's 1, 1, 1, 1. Nice, it's already balanced. So that'll make this second fraction easier. We have 1 mole of NaOH on the bottom, 1 mole of the perchloric acid on top. All right, and then for the final one, that means, okay, moles of the perchloric acid go on the bottom. We'll have 1 liter of perchloric acid on top. The molarity is 0.115 moles per liter. And then we're ready to punch this in. So again, anything on top we multiply by, anything on the bottom we divide by. So 0.05 times 0.0875, and then divide by 0.115. We get an answer of 0.0, let's see, how many sig figs? We want 3 sig figs, it looks like. 380 liters of the perchloric acid. Now, sometimes the problem will specify to make it milliliters again. If that's the case, just move that decimal back 3 spots. So we could say 38.0 milliliters. Either way, that's our answer. So you see, even when we're dealing with molarity, it's still the same 3-step process. It's still get to moles in the first step, convert between moles in the second, and then get to your answer unit in the third step. It's just now we have how many moles for every 1 liter whenever we're using molarity. I hope these examples were helpful, and I will see you again in Chapter 5.